Welcome to all. Now I am going to explain my PG project of an experimental and analytical investigation of geopolymer concrete beams with ceramic waste as fine aggregate. First of all, my main aim is to study the structural behavior of geopolymer concrete beams with ceramic waste as fine aggregate. Then the main objective of the project is to find the alternate binding material for cement because the production of cement emits large amount of CO2 which causes global warming. So in this project I am going to use a geopolymer as binding material in concrete and also to reduce the scarcity of sand by replacing waste material partially or fully by compactive material like ceramic waste. First of all, the what is geopolymer? Geopolymer is an inorganic aluminosilicate polymer synthesized from silicon and aluminum material of geological origin or byproduct materials such as fly ash. Then the ceramic waste. The major source of ceramic waste are get from ceramic industries and building construction and demolition waste. In this project, following materials are used in this project: fly ash, class F, fine aggregates, river sand, ceramic waste, coarse aggregate, alkaline liquids, superplastics as sulfonated naphthalene formaldehyde, commercial name is Conplast SP430. Fly ash class F, their properties are shown in table. The properties of fine aggregates like river sand, the properties shown in table, and their sieve analysis results also given. Ceramic waste. The ceramic waste are get from the local site, construction site, and it's converted into small pieces like hand tool like hammer, and it's converted its sand size by jaw crusher, the size below 4.75 mm, and their properties of ceramic sands are shown in table, and also the sieve analysis result. From this the IS 3841870, the grading limits of fine aggregates are 4 zones based on the percentage of passing. From this, the two fine aggregates like sand and ceramic waste fall in grading zone 2. This is the particle distribution chart of fine aggregates. And properties of coarse aggregate. In this I am using a 20 mm aggregate as coarse aggregate, and their properties and sieve analysis results are shown. And alkaline liquids. The two liquids are used. One is sodium hydroxide and another one is sodium silicate. Sodium hydroxide in flakes form and sodium silicate in liquid form. It also called as water glass. Another, the superplasticizer. Superplasticizer in this sulfonated naphthalene formaldehyde as used. The main function of superplasticizer is to improve the workability of concrete, and also it is known as high range water reducer. Before going to mixed design, following assumptions are made. The ratio of sodium silicate to sodium hydroxide solution fixed as ratio of 2.5, and the molarity of sodium hydroxide solution was fixed as 8 molarity. 8 molarity means molarity of NaOH is 40, so 8 into 40, 320 grams. To prepare the 8 molarity solutions, 320 grams of NaOH flakes is diluted in 1 liter distilled water. and the ratio of alkaline solution to fly ash by mass was fixed as 0.4, and the combined aggregates in concrete is assumed as 7.75 to 80 percentage, and the superplacer as 1.2 percentage of fly ash, additional water as 10 percentage of fly ash. This is a mixed design. Proportion of aggregates, the density of concrete. From this, get the combined aggregate assumed as 77 percentage. Get the combined aggregates and assume the ratio of coarse and fine aggregate as 0.4 and is to 0.6, and the fly ash and alkaline liquids, their masses are derived and based on the ratios assumed, and the solutions NaOH and Na2SiO3 ratio as 2.5. From that we get the solutions masses, and superposition as 1.2 percentage of fly ash, additional water 10 percentage of mass of fly ash. The ratio is 1 is to 1.8 is to 2.8. The total masses of material used in the concrete. It is the trial mix design. Totally 5 numbers of trial mixes used. First one is GPC, is the control mix. Remaining 4 are the replacing of sand by ceramic sand. By first one is 25 percentage, second one is 50 percentage, third one is 75 percentage, fourth one is 100 percentage. Then preparation of GPC. Before going to prepare the GPC concrete, we prepare the alkaline solution one day before of casting. First prepare the sodium hydroxide solution. By the flakes are diluted in distilled water for required quantity, and these solutions and sodium silicate are mixing together one day before because of the polymerization. After that, next day we prepare the GPC mixes. Then casting the in this mix casting the GPC mixes. For each trial mix 3 cubes and 3 cylinders. This is a compression testing machine and split tensile test. The results are shown in table. From this results we get that GPC2 mix like 50 percentage sand, 50 percentage ceramic sand give the lightly more compressive strength compared to GPC, and all, but the split tensile strength is not equal to the controlled mix. It's a graphical representation of compressive strength of GPC mixes. This chart shows adding of ceramic sand is increase the compressive strength of geopolymer concrete up to 50 percentage. Further increasing of ceramic sand is it will decrease the compressive strength of geopolymer concrete. It is the split tensile strength of GPC mix graphical representation chart. It shows the adding of ceramic sand will decrease the tensile strength of concrete. After that we found out the stress strain property of GPC and GPC2 too. The cylinder is axially loaded. From this we get the stress strain curve for GPC and GPC2. It is observed that stress strain curve for the young smallest for GPC plain concrete was 16 GPa, and GPC2 young smallest is 17 GPa. This is a beam design. In this I am using assume the dimension of beam as 100 150,000 mm and clear cover 20 mm, 8 mm steel bar used as reinforcement, and M30 grade concrete Fe 500 HYST bar is used. their effective depth are calculated, and then the neutral axis depth is calculated for rectangular section is less than the limiting neutral axis depth, and base, then it's less than the limiting value, so calculate the moment of resistance mu limit and mu. From this the mu is less than the mu limit, so it is the section is under reinforced. So provide two bars of 8 diameters bottom and two hanger bars of 8 in compression side. Then ultimate load, ultimate dead load, calculate moment due to dead load and moment due to live load. From this we get the total design load as 28.04 kilonewton and spacing as assumed 100 for stirrups. So geometry of beam specimen. The mold setup for GPC beams. Totally 4 number of beams are casted. 2 is GPC, another 2 is GPC 22. This is a mold setup with reinforcement, and the casted beams with mold, total demolded beams, testing of beam under 2-point loading, 1/3 distance the load is applied. The load deflection curve for GPC beams is observed that the ultimate load capacity is 80 kilonewton and corresponding deflection is 7.87 Their crack pattern shown in here. The load deflection curve for GPC 2 beams, the ultimate capacity is 85.24 kilonewton and deflection is 8.64 The crack patterns, summary of results. The load deflection curve characteristics of at midspan of GPC beams and GPC 2 beams were found almost similar. GPC 2 beam showed slightly more load carrying capacity compared to controlled GPC mix. GPC 2 beam showed slightly more deflection compared to the same loading at controlled GPC beams. The ultimate load capacity of GPT 2 beam is 85.24 kilonewton. GPC beam is 80 kilonewton. Next, the analytical investigation by ANSYS. Before we going to the model, assign the element types for concrete and reinforcement. For concrete, solid 65 is used, reinforcement link 180 is used, and assign the material model properties. First, material model number 1 is for concrete, material model 2 for reinforcement. Linear isotropic in this, their Young's modulus, Poisson's ratios input. Concrete, their compressive strength and tensile strengths are input. Multilinear elastic, their stress strain values are input. Their material model number 2, the linear isotropic, their Young's modulus and Poisson's ratio. Bilinear isotropic, their yield strength and tangent modulus are the inputs. This is the geopolymer beam model in ANSYS. Reinforcement diagram and support conditions, one end fix and roller support, application of load in beam, the deflector shape of beam. It's a crack pattern from the ANSYS. Based on the analytic investigation, the following conclusions are drawn. The control GPC and GPC2 predicted ANSYS are very good agreement with experimental results. The ultimate load and deflection values for GPC2 beams are higher compared to controlled GPC beams. The numerical study shows the ultimate capacity of GPC beam is 72.34 kilonewton and corresponding deflection is 6.57 mm. The ultimate capacity of GPC2B beams 79.87 kilonewton. Corresponding deflection is 7.08 mm. The comparison of results: experimental and numerical. GPC and GPC22. The experimental 80 and corresponding is deflection is 7.87. The numerical ultimate load is 72.34 kilonewton. The deflection is 6.57. GPC2 85.24 kilonewton ultimate load, deflection 8.64 mm, and numerical for ultimate load is 79.84 kilonewton. The deflection is 7.08 mm. This shows the numerical value is less than the experimental results. From this project, I conclude that fruitful utilization of waste materials such as fly ash and ceramic waste for the production of good quality geopolymer concrete. The production of geopolymer is gainful utilization of fly ash and ceramic waste to save the environment by reducing stockpiles. Thank you.